Well, hello and welcome to Are We There Yet? MarketScale's online video podcast series that explores the most exciting companies, projects, and technologies in transportation and mobility today. My name is Grant Harrell, and really fortunate to have the opportunity to speak with some of the most innovative companies, technologies, projects, and innovators. And really excited, speaking of today, to speak with Electric Goddess and to speak with us about the exciting company and projects that they're involved in. Really fortunate today to have Erika and Luke to speak with us. So Erika, Luke, hello and welcome to Are We There Yet?
Thank you.
Hello.
Pleasure to be here.
Hi. Well, thank you. Thank you. Well, really appreciate you taking the time to speak today and have been really excited to learn more about your company and projects and just so impressed with everything that you've accomplished in a relatively short period of time. So really appreciate you taking some time to talk today. And I think that battery technologies, battery cell technologies, EV, transportation, mobility, such an exciting topic in the world today, and have a lot of events and conferences, things like the Battery Show and EV Tech Expo that I know that we'll all be at here soon, coming up just right around the corner. So really just, I think, an exciting topic to be speaking about today. And so speaking of all of that, would love to maybe just jump into the Are We There Yet question, and would love to get some of your insights, Luke, regarding transportation, mobility, battery technologies that really are commercially viable and scalable to truly replace traditional technologies. Are we there yet?
All right. For a battery technology, what we use today is pretty highly scalable, right? With caveats being in NCM cells and NCA cathode cells, you run up on nickel as a limiting reactant in your supply chain. And in an iron phosphate cell, essentially it's lithium becomes a price factor, and it becomes a dominant material cost in the cell and supply chain limit from scaling. And fortunately, that's not because there's a shortage of lithium, though. There's a shortage of lithium production. And so, that challenge with lithium can be solved. But if you don't want to solve that challenge, the sodium ion is in, incredible abundance. And it works as a sodium iron phosphate battery, ironically using a graphite coating over a copper anode for your current collector, and an aluminum coated in sodium iron phosphate and traditional carbonate ester based electrolytes, and sodium hexafluorophosphate is your ion. It functions almost identically to a lithium iron phosphate battery, just with a sodium iron phosphate. So because there's no phosphate limitation, no iron limitation, and no sodium limitation, that topology could scale to replace, not only all the grids of the world, all the power grids to be stabilized of the world, but also all forms of transportation. One of the caveats being, lithium has a lower galvanic potential sodium has a lower galvanic potential than lithium, and so there's an associated lower voltage per cell while you're in the same range of capacity. So you have a energy density hit of around say 30-40%, maybe more. Maybe as much as 60%. It's actually complicated on a number of factors, but what phase you're converting the graphite into and how heavy you're, normally you'd call it lithiating, but this would be sodiating, I suppose.
So as far as transport, we're driving EVs now, right? Luke and I have electric motorcycles, electric bicycles, electric vehicles. And that's awesome. But I think what Luke is talking about is when it comes to mass producing the cells and the energy storage that we need, there's really that journey that we're all on with discovering the material science and the technology that goes into providing the electric vehicles to the masses.
It's also worth noting a sodium iron phosphate cell wouldn't have to be worse than today's lithium ion batteries, for the reason that today's lithium-ion batteries, most of all of the, you have a cell, let's say the cell weighs 68 grams, and of that cell mass, only a couple grams are actually active lithium that you're changing oxidation states on to provide useful energy from the cell, and all the rest of that cell's 68 grams, say the other 65 of the 68 grams is not related to the actual action of that stores energy. It's related to the infrastructure to enable you to change oxidation states of that lithium ion and then unchange it. It's essentially like you are burning a metal. You could see magnesium burn, right? It's almost like you're burning a metal, except you are able to unburn it because you didn't burn it in a way where it bonded. It was interstitially intercalated between oxygen valences. And so it was similar to burning, but you changed oxidation states just the same. And so if you were to be able to use, say, even 5 grams of that cell's mass to be useful ions undergoing reduction, not if you were lithium, you'd be double the energy density, right? But if you were sodium ion, you'd be as good as today or better. And for that reason is the reason I mentioned it doesn't have to be a penalty. It just is today if you use sodium ion with drop-in existing cell technology. But that's only because this is a relatively infantile stage of development in storing electrical energy.
Okay. Yeah. No, that makes sense. I appreciate that. You're certainly educating me a lot too on that process, but I think ultimately it makes sense. And do you feel that the sodium ion technology and process that you described is it necessary? Do you feel like maybe that's the key to really getting to commercial scalable, or not necessarily?
It's only necessary if you don't want to scale lithium production.
Okay.
Say that you view the salt pressed films in Bolivia and Chile and Australia and whatever as something not to scale up production for whatever reason even though if you're trading the atmosphere for it, it seems like a foolish trade to me. But let's say you don't want to scale production, then that's when something like sodium ion would be useful, because otherwise lithium iron phosphate, just with today's existing technology and manufacturing capabilities, makes amazing EVs, with long, useful, durable cycle lives. And it's only limiting supply chain factor, is obviously you need high purity electrolytes, as part of this material, but those are not material choked from scaling. They're only whether or not the factory wants to build an extra line or build an extra reactor, build an extra supply chain, but the input feedstocks are not restricted. So you could scale it to replace all the energy storage for the whole world quite easily that way.
Wow. Okay. Very good. And if you don't mind too, and that kind of probably bring a lot of this full circle, but do you feel like we're moving towards scaling production that would be necessary, with the lithium technologies, or kind of yet to be determined? As you shared, that's really the kind of limiting factor now. Do you feel like we're moving, to maybe start opening up on the production side of things more?
To be honest, I'm not a lithium supply chain expert to comment, but we do have a battery recycling company, and we extract lithium, as one of the many materials we harvest from batteries. And so the reason I bring it up is because it doesn't necessarily have to be a continuous burden of lithium. That's actually one of the easiest loops to close on the recycling, materials process recovery. So you would essentially need to mine enough lithium once so that you had batteries for the people in the world to do the things they wanted to do with batteries. And from that point forward, as they reached end of life, which something really amazing is a lot of credit to Jeff Dunn's amazing researchers and himself. But there's been proven many combinations to make electrochemical cells, including lithium ion batteries now, that have a expected calendar life in the, say, 100-year plus range, and have expected cycle lives. There's an example of a titanate iron phosphate, a lithium titanate iron phosphate. The research on the cells that they made, they stopped cycling it for time constraints at something like 5.5 million cycles. And that was, it still had nominal capacity. But the penalty of those cells is the energy density is only something like, say, 30% of today's NCM cells you might find in a Tesla Model S, for example. And so even though the cell would, allow you to recharge your car millions of times over 100 years of use before you need to replace your pack, you would have a third of the range. And so today's market isn't asking for a car with a third of the range and 100-year lifespan. But what it shows is that the technology doesn't have to wear out. If you have pistons going up and down in cylinder bores with, you've got your compression rings and everything, they need ring drag to function, to compress right, and to seal well. Your valves have to crash down on their seat and interface hard to seal well. And all of these mechanics means there's wear involved. Every time your camshaft hits whatever lifter element it's engaging, there's wear here too, right? So these things are finite, whereas a battery and an electric vehicle doesn't necessarily have to be finite in its use case. If you're willing to make the design cost and capacity compromises, you can do it today, as Jeff John's team has demonstrated with a number of cells. But the beauty is that since we're only using such a small percent of the size and weight of each cell for active lithium storage today, we will find out how to do it with, say, 3 times as much, 4 times as much, 5 times as much, and make it last a century and make it last megacycles. And, at that point, battery replacement will be something, it'll be life of vehicle.
Absolutely. Absolutely. Yeah. That's fascinating. I really appreciate that. Those insights. Yeah.
What's awesome is it's not a physics problem or a chemistry problem. It's a material science problem. It's an electrostatic and nucleation problem, electrostatic field stress and nucleation decay of electrolyte splitting molecules. It's the side reactions. Essentially what I'm getting at is the chemistry that you would write down in an equation for how a battery works, and you're changing oxidation states of lithium ion between graphite and a metal oxide complex, and in this function, there's no side reactions, and it doesn't ever have to wear out, and nothing has to go wrong. It's all of the effects due to impurities, due to surface irregularities, due to electrode irregularities, due to crystal irregularities. All of these things are what cause the decay mechanics to happen. It's not like it intrinsically has to wear out. A lead acid battery in your car has to wear out because the acid's reacting with the lead from the moment it's added. It's flipped its hourglass over. But lithium-ion batteries don't have to work this way. They don't run in an aggressive sulfuric acid electrolyte, right? We use carbonate esters.
Yeah.
Anyways.
Yeah. No, that makes sense. That makes a lot of sense. I really appreciate that. And I think that's very optimistic, positive outlook on it, in terms of it really reaching the battery technologies, battery cell technologies, being set up. The science is there, in terms of, replacing traditional fuels. We need to do, some improvements in terms of the life, as you shared, and kind of hit that balance between, the range that's necessary, with the lifetime of the technologies. And we'll figure out that more, as we go, it sounds like. But I think that's a really, really positive, outlook and insight to have on it. And I think really shows that, on the science materials side of things, production side of things, that it certainly is set up for success in replacing those traditional technologies. So I really, really appreciate that. So
Thank you.
Yeah.
From a manufacturing technologies perspective, it's kind of like, the days when we started to put, say, vacuum tubes together to form crude logic networks to make a computer, and once someone had built, one that used, like, say, 1,000 separate vacuum switches or whatever, they thought, like, wow, this has got to be the end of the road for this technology. Like, this fills a whole huge room and consumes so much power, to do this computation.
Yes.
But now, our smartwatch has, like, millions or hundreds of millions of transistors, in this network. And in the battery perspective right now, we make the best particles we can, the best uniformities and purities. Then you blend them with the right binders. You mix the slurry, you coat it, and you roll it. But the thing is this is kind of like the stage of vacuum tubes hand wired together in the room still.
Mm-hmm.
And when we begin to leverage, like I mentioned, in that cell, it's 68 gram cell, and it's 65 grams of material to help you change 3 grams of it to usefully do energy storage change, right?
Yeah.
And so, that's what
that's your margin.
Mm-hmm.
That's right. Mm-hmm. That's your margin to grow, right?
Yes.
You're using this much, so it's basically like we've only begun to investigate meaningful storage of electrical energy. Let's not forget if you have atomically precise manufacturing, all you need to do is make layers of graphene and barium titanate in perfect atom precise layers in a sandwich to form a plate capacitor, and to beat the energy density of gasoline by something like 8x. And on top of that, it's not even a battery, it's a capacitor. And so this is what, so it doesn't even need electrochemical reduction, right, to work. It stores an electrochemical charge of the dielectric capacitance of the barium titanate. But, the reason I bring it up is because that's a manufacturing problem. That's not a physics problem.
Right.
You could have a shoebox in your car that holds more energy than a full tank of gasoline for you, and you could recharge that shoebox. It's a capacitor. You could recharge it in 1 minute, and that would kind of obsolete batteries. But today, we only build atomically precise structures painfully slowly, a few layers at a time, and so to make meaningful energy storage devices that are, of that precision today, it's the same challenge of if someone said, well, here's your vacuum tubes, I need you to wire me up 100 million of them, please, and also put it in a practical location.
Right.
You'd say, well, there's no possible way,
yes.
right? But that's the lack of creativity of realizing the process that lied ahead, in deep ultraviolet photolithography, to etch, and selective doping, and now 3D doping and selective 3D etching. So once these processes were created, now it's a trivial thing, and even a dollar store gift card that opens to sing you a song has 500,000 transistors in it, right? And it's not a big feat today, and I don't think electrical energy storage, to hold all the capacity you would ever want for your application, will be a big deal either, as that materials tech and manufacturing tech. It's again, you're not pushing against a physics problem. You're pushing against what can you make for a reasonable cost that's safe enough for consumers to use and lasts an acceptable lifetime problem, right? And so, if someone's coming at you saying, I'm looking for, beating gasoline by some large margin to one, then, that's another discussion. You have to start at an atomically precise structure to get there, but it's still not a physics problem.
Very good. Very good. I love that. No, you look through that lens too. And I think, think of the example as you mentioned, and we've done it before. Why can't we do it again? The physics is there. So, just need to continue kind of that innovation on the atomically precise manufacturing, side of things, research side of things to make it happen. And I know that's very much what you do, what Erika does, and what the company does. I'm really excited to learn a little bit more about the company and some of the projects, but, I would love, I think might be a good kind of, segue, speaking with you and with your incredible insights, in terms of kind of moving towards commercial viability. I'd love to, learn from you, Luke, how you got in the space. How did you get into, working with Erika and the team there, and into the, battery cell technology things? Would love to learn a little bit more about your journey to where you are today, if you don't mind sharing.
I'll try to make it brief. I did data center megawatt scale UPS cooling and power work for Microsoft, and it was it introduced me to megawatt power transfer, which was new to me at that time. And after Microsoft, I left to go to Zero Motorcycles, and this was a radically different environment. A data center is vibration free, it's temperature and humidity controlled. So basically anything that you build has no corrosion issues, no vibration issues, no resonance issues. So it was like doing batteries on Easy Street. And now, at Zero Motorcycles at that point in my life, I learned a lot of, basically the R&D curve was so difficult. And I think what helped the most was being foolish enough not to give up. And, there was a period of time for a couple of years where I would work every day from the moment I woke up until exhaustion late at night, and closed Zero down, set the alarm. Like, there was actually a problem one time when I didn't close the alarm because people didn't know how to set the alarm. People that left. Right?
Just knew you were going to do
it. Yeah, like, why did he leave before?
Right.
Yeah, but anyways, I worked like that because we had to get to production with a safe product, and in validation testing, you would find concerns. They call it engineering discovery, right? And so it was a long chain of repeatedly test as fast as you can try a new design to test. And what got through it was not a stroke of brilliance or anything. It was not losing the drive to stay creative and to continue to try testing, and eventually things worked. We were able to enter production, and it was, a huge weight off my shoulders and the rest of the team's shoulders. And after that, the process to do it was difficult from a manufacturability perspective. It worked. Like, they lived in the wild and they were safe, but they were difficult to manufacture. And so I spent another 4 years or so there working on manufacturability to make them simple and pokey-okey and essentially unable to be manufactured wrong is the goal, knock on wood. But after that, I left because I realized the rest of the industry was just now starting to learn these challenges that Zero had a head start on, having been an EV company that founded in like 2007. And so it gave me this drive to help share the things that I'd learned to protect EVs, to survive in the wild, to save waste, and to save EVs getting a bad reputation too when there's events. It hurts the whole industry. And I had moderate success just as a single freelance scientist with a backpack of tools. And I was blessed enough to meet Erika while working at Romeo Power, and she was a program manager there. And at some point, we realized we were far more powerful to combine forces than the sum of our components. And I'm so grateful. And it's a good time for her to introduce herself too.
Yeah, well, thank you. What incredible story and journey, and inspiring. And gosh, you're doing a lot of good along the way as well. Just helping the companies and sharing some of those insights that you had. And what a powerful partnership, as you shared with you and Erika. And I think you demonstrate that every day through the great work that you're doing. So would love Erika to learn a little bit more, about you and the company. As I shared, I've just been so impressed as I've got to know you and Luke and learn more about the organization and all the really cool projects that you're involved in. Do you mind, sharing with me and audience members a little bit more about Electric Goddess?
Of course, Luke is being so humble. I always enjoy that about him, with how much he's helped the world. I was I was blessed to start my career as an intern working on the Dragon capsule at SpaceX, and I got to meet a bunch of incredible people and learn that work drive that really, Luke learned it in a different way, and I learned it with having a golden star or a North Star mission and working towards that and having that clear. And then I joined Romeo Power when they were just a factory that was empty, and I ran new product introduction. So that's all the way from R&D into customer deliveries. So I helped with choosing the equipment, setting it up, building products, testing, everything, and got an education that I feel so blessed to have, because I know it's very in demand. And I kept getting promoted, and then was running a joint venture with Borg Warner, or helping run it. And that's where Luke and I really got to see that global perspective on how much batteries are needed from a large corporation perspective. And we knew that there are startups out there and even large OEMs that really need the guidance and the knowledge that we have. And so Electric Goddess was formed, and it's a really fun business name. We have kind of polarizing views on it. Some people are like, this is really shocking. And other people are like, I love it. And it has been so fun to do all the way things from communication satellites, electric aircraft, electric VTOLs, all the way to like jet skis and power sports and electric trains. And if it has a battery in it, we're very interested in helping you on your specific application, because there's not batteries that are one size fit all. And that's what kind of drives Electric Goddess to be a battery consultant, but then also have an analytical test lab, because there's technology's changing so fast, and we need to be able to stay on the tip of the spear and test the new products that are coming out and be able to give the advice to our clients and do the tests for our clients that help them stay ahead of the curve as well.
Definitely.
If I can comment on the test that we do too.
Yeah, of course.
We kind of focus on the niche of the tests that other labs turn down.
Okay.
So having 12 years in industry working with batteries and being on the side of calling other analytical test labs, and saying, hey, I need this. We learned which ones you can call them all. You can have a blank check, ready, and you can't get a test ran. And so of particular tests, there's some tests that are either very technically difficult because the odds of the signal to noise ratio you're looking for is very small, let's say, or say it's a thermal impedance measurement that's very difficult, or it's too dangerous, or a work health safety hazard sort of concern. Say that even with exotic PPE, you can't protect from the hazard. And so we actually built some very specialty equipment flavored specifically around hitting all these niche tests that the other labs turned down, including, to our knowledge, the world's largest thermal runaway calorimeter for batteries. Our calorimeter, it's 1.5 inch thick, 316 stainless steel, and it's something like 3,500 pounds.
We actually used old, I don't know if Luke will like me to say this, oil rig equipment to use it for testing batteries, which we found to be like really cool in the life cycle.
The stainless body of the calorimeter we test batteries in is a high pressure oil pipeline refinery strainer basket holder.
Wow.
That happened to be 316 and the right dimensions and size. And then we welded and modified onto it to and added the heat exchanger stack. Of course, it's just the lower pressure vessel.
Yeah.
Electric Guys comes from humble beginnings, right? So Luke talked about a backpack, and when I met him, he just owned a motorcycle and that backpack. And we started in an extra bedroom of an apartment. And we had people coming in and be like, why do you have so many power supplies in your extra bedroom of your luxury apartment? And then from there, we hired our first employee, and he was the one who kind of helped us encourage to get a space, right? Because that was...
Before we hired an employee, we had to do many jobs to get income first when it was just Erika and I.
Yes.
But once we had success, we were growing with no marketing either, just by word of mouth referral. So as grassroots as it gets.
I quit my corporate job on a Friday, and on Saturday we got a call saying, hey, can you come to New York? And we're like, I guess this is the universe taking care of us.
No kidding. Meant to be, I would say. Gosh, how cool. That's incredible. Well, that's so inspiring. What a just a really cool grassroots, just kind of get it done, starting from scratch, really, into what you've become today. I think that's just even more inspiring. And how ironic that you're using some equipment, from traditional oil for the latest, coolest stuff in EV and electric and battery technologies. I think that's a lot of fun too. So
even better, our one of our R&D labs is right next to a giant oil refinery.
Oh, perfect.
And I think it will be our battery recycling facility. Because many of the vessels there are useful for digestion tanks, electrolyte distillation tanks, fractional distillation to separate things. So anyways, there's a lot of equipment there that when we don't need them to be processing gasoline anymore,
Yes, perfect.
Yoink, battery recycling facility.
You strategic location. You're already thinking 5-10 years out on the location. So I love it.
Yep.
That's awesome.
Just got to cross the street and we're there.
Yeah, you're a very long-term thinker. I like it. No, that's cool. Wow. Well, okay. So fun question. I'd love to maybe get some of your perspective, Luke. So you're involved in so many different mobility transportation methods and everything from scooters and paddle boards and EVs and everything else. But maybe talking EV automobiles for a second. If you're on a drag strip, which do you prefer to be in? Do you prefer to be in an EV or traditional vehicle?
Okay, it's funny you ask that because my grandpa was a drag racer and one of the first people to put Detroit diesel 871 series blowers on gasoline engines. And
Okay.
my dad was a drag racer and a hot rodder, and I was also a drag racer and still a hot rodder.
Wow.
And I got to say, I can't tolerate interruptions in my torque delivery anymore.
Okay.
So, you know, the loss of time and shocking the tires too. You know, if you're going to have a car that shifts, each time you shift, you shock the tires again. You know, so you had to be at under max traction threshold of, you know, under max slip rate before you shift.
Yeah.
And then after the shift, you know, you shock the tires again. So you got to, you know, anyways, you have to like make these soft places in your boost curves. You know, and that's bullshit.
Mm-hmm.
There should be no soft places in my acceleration. That's why pure EV for me. Also, I hate breaking transmissions, axles, clutches, and I have shredded so many sets of drivetrain components. You know, I used to go to the track with 2 spare axles, and sometimes I'd still get pulled home on a tow strap, one for each side, but you'd break your spare. And you know, this is because you're shocking the drivetrain. So the internal combustion engine intrinsically makes 0 torque at 0 RPMs. So to get your launch to work, you know, you store kinetic energy in your crankshaft. You know, I would launch on a 2-step limiter at 10,500 RPMs. And on the clutch drop with this twin disc clutch, you know, it grabs it and it shocks this kinetic energy. And it's kind of up to the luck of the draw and how your ankle, you know, engaged that shock to control the magnitude of the time constant between the crankshaft locking up 1-to-1 through the slip of the disc, you know. And so because of this shock, you know, it's not good for your launch and it's not good for your drivetrain components. You know, it's basically I DNF'd half of the drag events I entered with my gas race cars. And part of that is from running too much nitrous or too much boost because you get excited at an event, you know. But in an EV, yes, I've blown EVs up too. You know, you can blow your EV motors up, you can blow the controllers up, but you don't have to, you know, I've never had to replace a transmission or powertrain parts or axles, you know, and like, yes, that's, you know, never want to replace another transmission. Like,
Luke has the fastest electric bicycle in the world. You can look up Death Bike on YouTube and you'll see him racing Teslas.
Yes. Okay. And that's Luke.
In the full quarter mile too. It actually is faster than a Ferrari Enzo in the full quarter mile. And that's my electric bicycle. Wow. So you can see why I would be disappointed in gas car performance, you know, if like, my pedal bike, you know, is slower than an Enzo or is faster than an Enzo, you know, then it's like, why do I want all the noise and jerking interruptions and mechanical failure modes that frequently occur, as I know, having a history of drag racing? You know, so like you can just drop all of that and just be fast with all the torque the tire can hold at optimal slip ratio all the way down the quarter mile. That's how I want my runs to be now.
For sure, for sure. Gosh, well, that's incredible. God, I'm so glad I asked that question. I think you might be the most qualified individual in the world to have answered that question officially for us today here on the podcast. So gosh, thank you so much. I had no idea the background and from generations of drag racing.
When I was in school, I wanted to be a Formula One engine designer. And I would say the mentor I guess I did learn the most from in life is Larry Widmer of Indyne Motorsports, you know, which does energy dynamics. It's a race engine tuning business, you know, and I learned my thermo and fluids from race engine tuners, and now I apply them to electric vehicles, and you know, feels like shooting fish in a bucket from you know, the difficulty perspective difference. EVs make torque and horsepower so much easily, you know, like hot rodding has never been better than electric vehicles. You know, if you like ridiculous overpowered hot rods with insane acceleration, like you should be an EV fanatic. You will just be disappointed in that pursuit with gas engines.
For sure, for sure. Wow. And I love that you learned it from your experience too. You didn't just jump into the newest, fastest EV and, you know, yeah, it's fast. You know, you've been there, done that with, it sounds like, you know, all sorts of different types of vehicles and traditional technologies and maxed them out, you know, with all of the work that you did. So you really have an appreciation, it sounds like, for EV. And of course, to be very involved in that space right now, that's really cool. So, wow. Well, you've officially answered it here on the podcast related to that. And I'm sold. So I think I'm going to need to go EV, you know, on the racing side of things now, it sounds like as well. Would love, like I said, that y'all are involved in a lot of other methods of mobility and transportation as well. And I know that you're doing a lot of really cool work at e-bike space. As you've each shared, electric paddle boards, EVs, VTOL aircraft. And so would love to maybe just get, kind of an overall perspective in terms of, and I think you kind of answered this already with some of your successes, but, I was curious, within talking about some of those other methods of transportation, are battery packs, battery cell technology, is it working? Is it safe, in some of these other methods of transportation? So would love to, get any insights that y'all might have on that as well.
If it's a pack that we designed and validated for our clients, then yeah, I can say it's safe. It's so safe. We shoot, say, 5 3-inch nails into them while they're preheated to max temperature at 100% state of charge. We initiate overcharge runaways. We initiate every type of propagation, even laser-induced propagation and some other creative methods, to start thermal runaway and validate that it doesn't spread cell to cell in a chain reaction that just that consumes the whole pack or the whole vehicle, right? So we do tests where you pass something PPR, passive propagation resistance, meaning with no outside interference to help fire it, fire extinguishing, no active methodology, right? Just initiating runaway with no helping the battery, and it self-extinguishes and does not propagate.
Wow.
And so, yeah, even in those situations where in the extremely uncommon, cell defects today are almost non-existent, in lines that are set up right, and like somebody didn't put the die in backwards, or like some grievous error in the line, right? But cell defects that cause fires are extremely uncommon. What's common today is packs that don't adequately protect from corrosion, vibration, chafing, resonance, and material compatibility, dielectric decay. There's some teething pains in industry right now, and unfortunately, I think there's going to be folks that still continue to learn lessons over the next few years, particularly the highest voltage systems. We do dielectric decay tests on different dielectric materials where you impose electrostatic DC fields across these materials and monitor how they perform mechanically and electrically over time. And it turns out many of them don't like DC. The reason why so many dielectrics work great with AC is because it has an equal and opposite electrostatic migration field, because its AC wave is positive, 60 every 60 times a second it switches from positive to negative, and so there's a net zero field. But in DC high voltage situations, there's a net positive gradient, and so even when you have mega ohms of isolation, there's still, even with 1 volt across your dielectric with mega ohms of isolation, there's still millions of electrons per second flowing. And these are the electron cascades that move ionic migration through, which scissors bonds in polymers and dielectric insulator materials, causing them to degrade, and change electrical properties and mechanical properties. So I think, yes, there'll be some tough lessons in industry, but fortunately, at least, it can be done so safe. Just like I mentioned, a battery can last a century too, or longer even. That's just what they're extrapolating. But it's one of those things that, like, how safe is cooking in your kitchen, right? Like, cooking in your kitchen could mean like you just open some pre-made meal, pull the plastic film off the top of something, right, and like you're done. Or it could mean you're using a bunch of knives and mixers and flame in a pan, and whatever else you're doing. Right? So,
yes.
Batteries as a thing is, you can definitely make hazardous batteries, and unfortunately, there's a lot of folks in industry still learning these lessons. But at the same time, it's good for our business, I guess.
Yeah.
Because we get called to solve these problems.
Yeah.
Not so good for the world, though.
Right. Because it's good for our recycling company, though. It's funny. Yeah. Why start a recycling company? Maybe because we know how the industry designs their paths.
Yes, absolutely. Well, it's good to know you're protecting the world, I think, in the work that you do, and you're making these technologies, for clients that you work with, safer. And so I think that does really just point to the great work that you're doing, and the world very much is benefiting from that. So that's great to hear. As you shared, you work in a lot of these different areas. I know that EV, of course, is a focus of yours. And would love to maybe too, get a little perspective from you, Erika, in terms of, EV companies, really avoiding recalls. Do you mind maybe commenting on that a little bit about how, these EV companies out there, can work to avoid future recalls on technologies?
That's a really good and big question, Grant. I want to start with saying that Luke and I, being with Electric Goddess for 3.5 years now, we're a relatively young company. We are establishing our, I guess, credibility to the larger world, right? People who know us and we've worked with them, like they know who we are, they know the work we do. I get that. But when you are, let's say when we first started, we went to the battery show and you're talking to large OEMs and you're talking to engineers and they're telling you about their pack and you're saying, well, these are the things I would test and these are the things that I would look into because I think that you're going to have a problem in a few years from now. They may not believe you, right? Because you're like, who are you? You're coming out of nowhere and you're telling me I'm going to have a problem in a few years. And the crazy thing is that those same people, I wonder if they think about us ever when, we're reading those news articles of things coming out and we're like, this could have been avoided. And so that's why we're talking to you now. That's why we do our podcast. That's why we're getting more information out there, is because we just need more people out there in the world starting to understand these concepts, that batteries are, like I said earlier, just not one size fit all. So you need to understand your application. And you need to not only just go off the test standards that you need to do to check a box for your insurance or for shipping it, but you really need to think critically about testing to failure and understanding your margins on when does it fail and how does it fail. And I think that that'll help the industry a lot instead of kind of just ignoring the blind spots, but maybe they just don't see it.
Creating validation testing suited towards the application too, because like Erika mentioned, a lot of folks do the test to check a box for a shipping standard or whatever, but that has nothing to do with whether your product lasts in the field or not. That's a shipping standard, right? And so it's when you create a validation process where I love to instrument real vehicles in the field, whatever they've got, if they've already got a product, you instrument it that way. You have real G data, real shock data, and use it. Use it as hard as the hardest customer you could imagine using it, and log all of those operating conditions. And then you can build a validation program that's not blind and not somebody in some academic writing random values in the dark to make a standard. Which is unfortunately how a lot of standards get built, and it may have no relevance on whether the product lasts well in your application. But if it doesn't last well, then you have a recall, like you mentioned. And so if you don't do validation testing, you get recalls. And if you do validation testing, you have to be creative enough to think of the real test environments and situations the product will be imposed on and find ways to test them and confirm that you have safe behavior. It's okay if a product stops working. It's not okay if a product takes homes down, right? And so this is why safety testing, for a lot of products, if it's like, a piece of consumer electronics that if it gets left in the rain, it doesn't work, and that's the end of it, too bad, so sad, right? Nobody cares. But if it gets left in the rain and then it gets parked in a garage and it burns the home down, now it's not, it's a different level of recall. You actually have to get them back. It's not a matter of, we'll mail you another one, or whatever if your ear's broke. But in this situation, it's critical. And so to ship without adequate validation is how to get recalls. And even in that validation, it's not going to be by some letter of some standards. The standards, sadly, are kind of a, I'm not going to say they're useless because they're a benchmark of something, right? There's someone's line in the sand they drew. Unfortunately, I haven't found situations where it correlates with the wild, meaningfully. And you can obviously pass the standards, check every box passing the standards, and ship a product that is recalled quickly, like an example of the GM Bolt pack, right? Went through, I don't know the exact number of millions of dollars in the testing program, but I think it was over $100 million in testing, right? And then you ship it and it dies in a couple of years, and that's, complicated effects. Batteries are complicated.
Yeah. Yeah, it is very much so. And I think, as you said, the stakes are much higher, than they are in consumer electronics and some of the other areas. So a little more of that validation is needed. I think standards, just as you shared, that are thinking maybe a little bit more long term and aren't just someone's line in the sand, as you mentioned, and something
That's
maybe
right.
the industry and professionals such as yourself, can maybe agree upon in terms of what's really important to focus on. So I hope that especially some of these big companies out there are listening more to you now, and I hope that the ones that you spoke with a few years ago now are thinking of you and hopefully using that in development of their future strategy and maybe taking all of this a little bit more serious. But nonetheless, I think the industry and all of us are very much benefiting from the work that you're doing. Talking a little bit about the work that you're doing, and I think that you already, each of you have commented a little bit on this, and I love this idea that you kind of pick up where other testing companies, kind of fall short, or testing that they're unwilling or unable to do, and a lot of times
unwilling.
Yeah, that's the opportunity, really, I think, to work with you. And again, I just want to share too, I think what a valuable proposition it is for companies to work with you and to benefit from that experience, because I think just in the the 30 minutes or so that we've talked here today, it's very apparent that you each bring some incredible real world experience, especially going back to really the early days of the industry. And so for a lot of these companies, rather than starting from scratch or even starting from 5-10 years ago, just so much value, I think, in working with each of you to bring some of those insights into the company, and even just to complement, what they're doing already, through a relationship with you, really seems to make a lot of sense and help them, to develop more long-term solutions and safer solutions. So I really see the value in that. But again, you've commented on this a little bit, but, I would love, if you don't mind, maybe sharing a little bit more of insight into, maybe just a general description of the type of companies that you typically work with, that you like to work with, that maybe benefit from working with you most. Do you mind, sharing a little bit more about who these companies typically are?
I'll let Erika answer it after I give a kind of funny part
Yeah.
here. For me, we only accept jobs for our whole company. We only accept jobs for devices that we would want to use and be used on us. And so we don't accept devices that are destructive or things we wouldn't want to use against us or on us. And so that's our first cut on what companies we work with. But from there, I love to work with the ones that have some challenge that's never been solved before, or they're up against something that's so insurmountable their in-house engineering team has already spent 6 months to a year spinning their wheels on it and millions of dollars. And those are my favorite ones to get. But I'll let Erika give you from the non-scientist perspective, which companies are good to get.
It's so interesting to have a staff that needs problems so difficult. They're always on the the cusp of like a mental breakdown, but euphoria,
Yeah, right. He just wants the challenge. Just give me the most difficult that they've already invested millions of dollars and years of work on, and I want those projects. That's incredible. Yeah, and challenging, I would say at the same time. Sure. Yeah.
I always found when I worked not at this company, now we just do really hard R&D, which I love it. But when I didn't work here, I was like crave the days at my jobs where I was doing really hard problem solving, and like the days where you had a known outcome of success as achievable, I was like, like just much less inspired. I would way rather have someone saying this is undoable and unsolvable as a problem. In fact, many of the jobs we've taken, when the job was initially presented, my knee-jerk reaction, thinking about the physics of the situation, was that it probably isn't possible. And then after 15 to 20 minutes or so, you see a glimmer where maybe on paper it is possible, and then once you've got a glimmer, you got to chase that glimmer, make a telescope and zoom in on that glimmer and find a path to it.
I love it. So an ideal project is one for you that seems impossible at first, but after a little bit of analysis, there's a glimmer of hope, and that's when you say yes. Yeah.
That's definitely a Luke answer. And we like that.
Yeah.
Electric Goddess fits as a nice addition to existing R&D teams, existing engineering teams, as just an outside perspective that can help the team give perspective on what we've seen in the industry, because we've worked on so many different things, right? So it can apply to equipment makers, it could apply to polymer makers, like not even just batteries. There's all the different material science problems around what goes into a battery and how you test batteries. And I just really enjoy working with optimistic people that have that same kind of North Star as us, that see that our role here is to do the best we can to help the world transition and change paradigms from this kind of dirty energy paradigm that somehow took over the past 100 years and transitioning to the next one where we have a glimmer of hope that we can have drinkable water and clean air to breathe.
Yep. And we got to stop treating the air like an unlimited dumpster, because if we do that, we will, that has a conclusion, right? Like you can fast forward time and see what that leads to. And it's breathing dumpster air, right? And everybody's dead. So we can skip that. We're smarter than that.
Absolutely. You already know that outcome, right? We all do.
Right.
Yeah, for sure.
Right.
So we've got to make a move in the other direction. And I really think this whole conversation for me has been so positive and optimistic and insightful that this other direction is the way to go. We can do it. On the battery cell technology side of things, the technology's there, the physics is there. It's really getting more into the production kind of optimization side of things. So that's
the electricity's there too, because we're not limited on the amount of solar panels we can make. It only takes something like don't quote my numbers here, but I think it's something like a 10 mile by 10 mile square dedicated to solar to power all of North America. And the crazy thing is, you might think, oh well, that the budget to make, because a 10 mile by 10 mile square is 100 square miles. So you have solar panel, it's a lot of panels. I think, well, we could never do the budget to make 100 solar panels. But I heard someone say that it could be done for 1 year of the U.S. military budget cost.
Mm-hmm.
And so that would mean you had all the power for all of North America.
Yeah.
In it, it's not even taking up a large amount of country. There's probably people's ranches in Texas that could hold a 10 mile by 10 mile square and they wouldn't even care.
For sure.
But
for sure.
Anyways, if you had that big of a solar farm, then you wouldn't want something like I mentioned, the sodium iron phosphates. If you scaled lithium production, you could just use lithium. Lithium's a fantastic ion. Small atomic radius and intercalates well, high galvanic potential. Basically, lithium is definitely better than sodium in every way, other than that we have unlimited sodium without any supply constraints today. Whereas we do have a ton of lithium, we just have supply constraints.
So I guess the question of are we there yet is a lot of people are struggling on which direction are we going?
Mm-hmm.
That's right. Yeah. If half the people are clinging to one method and half are, resilient to change and half are pushing change or whatever, then you kind of have a net zero difference if half of them are running. Anyway.
Yes. Yeah.
But the cool thing is that every year, you see the percentage of our grid that increases, that solar, and now it's becoming solar and battery stabilized. The whole Tesla Powerwall being commanded as a group thing that they're doing now. It's something like, I don't want to get the numbers wrong. I don't remember how many megawatts it is now, but basically this is just home solar can replace peaker plants, in this aspect, or even if it was in, evening without sun coming in, right? And there's the right home battery storage, then you can just use the same transmission lines that they deliver power to your house with. You deliver power to the power company back through them, when the power company needs it. And now the natural gas peakers are obsoleted. The power companies that we talked to when we did some grid stabilization work, they don't even like having peakers, and they don't like having to fire them either. That's why they put in such high price bids to run the peaks. It's because the thermal stress of starting the engines, those big turbines will last forever running at a steady output because they slowly ramp up their thermal shock and thermal expansion gradients, puts very low stress through their gas exchange, heat exchanger assemblies and everything. But when they go to peak, they start from just pre-warmed to making power in 6 or 7 minutes or whatever their peak delivery time is. And as a course of this, they put big, expansion stresses, from not asymmetrical temperature and all their, exhaust stages of their turbines and things. And so this causes, they don't want to do it. They don't want to peak. They'd way rather have something that peaked for them, so they don't have constant maintenance and high cost, to deliver those peaks. And so for batteries,
Yep.
batteries are like Mr. Peaker, right? Like they're all about power.
Yes.
They want to give power in a millisecond. They don't have a 7-minute wait. They're like, how about a microsecond? You want full power, right? That's how it works, and it doesn't degrade from that either. Like the turbine plant, when it fluctuates power, you can slam power into and out of the battery, as hard as you want, as fast as you want, and that's not a mechanism that causes artificial wear, unlike other things we use to stabilize the grid that involve burning natural gas or other things for peaking.
Absolutely. No, I love that. Yeah. And I think what a great way to kind of bring all of this, I think, kind of full circle. So, certainly everything I think that we've talked about today, it's not even just limited as huge of an area as transportation and mobility and everything that we've talked about there, but, it really gets into, the ability to get more into some of these renewable energy sources, as you mentioned, and, set the grid up, for success with some of these technologies and methods that are just, in and of themselves, better, for those types of things and peak demand and everything. So I think those are some great insights, to bring all this together, I think, in terms of kind of going in that right direction that we all want to be headed on right now. So I appreciate the insight on there as well. And, as we've all talked about today, I again, just am so impressed with what you're doing. Love that you're making the world a safer place. Love that you're sharing some of these insights, with your clients to help them, to really make their technologies better. And so I know that already so much demand in terms of companies that are working with you. But if you don't mind doing so, I know that as a result of the interview today, and we feature this at marketscale.com, the top business-to-business media platform today, and Apple Podcasts and Spotify and all the major platforms. So I know as a result of this incredible conversation, there's going to be a lot of individuals and a lot of companies out there that are going to want to learn more about the company and working with each of you. So if you don't mind, do you mind sharing website and maybe how best people can reach out and explore working with each of you in the company?
Only if they're stuck on something really technically
That's
difficult.
a caveat, right?
I'm just
it's got to seem impossible, right? Yeah.
Yeah, it's got to seem almost impossible.
Yeah.
No, actually, it's really good for the earth if we get involved early, because we can help you with material selection that won't be a hazard in a few years, and that can be extremely valuable, even though my preference is really difficult science.
Yes.
We have engineers and scientists on staff, though, and we're more than happy to help. And Luke is right. Starting earlier saves the business more money and helps the planet in the long run. Our website is electricgoddess.co, and you can reach out to us and schedule a free introductory call for 30 minutes where we can talk about your project and see where we can go from there.
That sounds perfect. Well, very good. Well, you heard it. Please do check out the website. And again, Luke and Erika, just really appreciate each of your time today. All of these incredible insights. This has truly been one of my favorite conversations on the podcast series. And I've learned so much, as I know many audience members have as well today as a result of the conversation. So thank you each, so much for your time, and wish you nothing but the best of the luck in the future, and look forward to continuing our conversations and working together. But thanks for taking some time out of your busy schedules to speak with me today. Really appreciate it.
Thank you. This was
pleasure.
fun.
Yeah, thank you.
Thanks for the opportunity.
Of course, you're welcome.